calculus of power series. So as I mentioned before, it is one or if not the highest point of the course. Seeing series seeing functions as series and series as functions. And so that's we reached the point when to demonstrate that it is really not just algebra of power series up to this point, but also calculus. Calculus meaning differentiation integration. How do we differentiate integrate power series term by term, as long as they converge. So if we stick within the interval of convergence of our series, we have then we are okay to do this. And for the exponential function in particular, its series converges everywhere. So whatever we do is fine term by term, and it will be every x will be available. Okay, so that's how we did it. So started with exponential function, found its power series, differentiated, realized that the power term by term, the series that we have discovered, that line over there, is nothing but the exponential function itself once again. So if we did not know, so once again imagine that we did not know from calculus 1 that the derivative of the exponential function base e is the function itself, then we would have discovered it right here, okay, in this manner, okay, which is a bit why we don't never do it, because the logic is kind of circular, because you cannot find the power series of the exponential function without knowing all of its derivatives. Remember, Taylor series required you to know for a function, it requires you to know all the derivatives of the function, all of them. Okay, so which means that in order to establish this, you have to know all the derivatives, and then you rediscover that the fact that indeed the derivative of exponential function is the function itself. So that way the logic is circular. It is when you realize that it doesn't matter what that function is, and that part about recognizing a function is really in its series is not really the way the idea that we care about. Then you see a point of this. So the example is it was at the very end. What happens if we start with that bell curve function, and by substitution we found its power series representation. Okay, so that power is actually skips one, and then we need to know its integral, antiderivative right there at the bottom, and then we are integrating it, and we ending up with a power series, and at that point there is no next step. We do not find its what function is it, and none of the familiar functions it has this power series. So it seems that it doesn't work out as well as with the last example, but it doesn't matter, because if we think that series are as good as functions, then this is as good as a function. Because why? Because for every x, this formula gives us the way to compute the function, the value of the function. Plug in, evaluate as many terms as necessary to achieve the accuracy that you want. That's it. Okay. So let me just summarize this statement in the form of a theorem. So differentiation and integration of power series, term by term differentiation and integration. That's a long name of a theorem. Term by term differentiation and integration of power series. So the only assumption that we need is that our radius of convergence is positive. So when it is 0, then there is nothing interesting we can do. It's like the function defined at a single point. So we cannot differentiate a function defined at a single point. Okay, so suppose r greater than 0 is the radius of convergence. Remember, it is usually found through the ratio test or the root test. So the radius of convergence of the power series an x minus a n from 0 to infinity. Okay, so that makes gives us a function. So the function will be defined on the interval of step r to the left or step r to the right from a. Okay, so like this, which, well, could be infinite. Not that. Okay, so this is a minus r, a plus r. Everything is good inside, as we have seen this before. Outside is bad, but it doesn't matter as long as the we are staying inside. We're good. So r could be infinite too. Could be infinity. Okay. So all right. So and then so there are two steps. They are number one first. F of x, well, number one. So f of x given by the series. I'll probably just write it f of x equal to the series, even though I'm rewriting the exact same formula, but there is a point here. So and then we now characterize this function in two ways. So the function represented by or given by the power series. Number one, it is differentiable. So is. Number one, differentiable on this interval, a minus r, a plus r. And its derivative's power series is, as we know, simply differentiated term by term. So let me put it this way to emphasize the point that we're looking at the term by term, and then we differentiate it term by term. So the term by term, what is a term? This is the term, x minus a to the nth power, to the nth power, and then I put a parenthesis here. Well, in fact, let me make even bigger point here. A question?
Yes, when will we use this in like real life?
I don't think you can. I don't know what your real life is, but if you're doing doing any physics or engineering, then yes.
Like, give like an example.
An example, I was going to give you an example of how you solve differential equations with power series.
Differential equation.
Yeah, yeah. The most typical, yeah. So if you take differential equations, that's a good place to be. But I think even up to now I can just repeat the point itself is that not every single function can be represented by function by formula by familiar function. So you have like in your calculator, engineering calculator, you have all sine, cosine, exponential function there, and you can click on it and you have that function. But that will cover only some small part of all possibilities. The possibilities that you do not know, even if up to now every single function you put on the list and you can handle them without power series, you don't know the future. You run into a function that you have never met because you're studying something new and you never done before. The function is not familiar, so what do? This is what you do. Okay, so you still, everything still works out. Even though the function is totally unfamiliar, it is irrelevant. Everything is taken care of as long as you can the function is well behaved. That's a requirement. As long as the function is differentiable enough times, then you have your power series, and then you can do calculus with it. You can solve differential equations, which we're going to have an example in a minute, and you can integrate. But mostly, I have to say, differential equations, that's the most straightforward example of how it works out. So I differentiate term by term. So literally, I carry out this differentiation. So I'll have a n x minus a n minus 1. So if it was a polynomial, by the way, the degree of the polynomial will go down. But because there are infinitely many terms, then no, there will be still infinitely many terms, and the degree is not really something to worry about. The going to happen just like with every function. The very first term will disappear because it's constant. Derivative of it is equal to 0. So in that sense, to correct myself, let me make it more dramatic like this. There is no, I cannot have n equal to 0 there, because n equal to 0 will give me power -1, right? And we cannot have a -1 power. So the 0th term is a constant. You differentiate it and it disappears. Right. Okay. So it is different for now the second part for integrability. Number 2, integrable on the same interval, r a plus r, would be infinite, and its antiderivative or antiderivatives power series is integral f dx. Once again, a point term by term integrated from 0 to infinity. Integral, well, once again, let me make a big deal out of it. dx of my term here, an x minus a nth power. Okay, so now if I carry out this integration, what's going to happen is, so summation from 0 to infinity, and what's going to happen to the power goes up, so I'll have and I'm applying the power formula again and again, because there is nothing else, only powers are present. So this will be n plus 1, and that's it. Yeah, I don't have this in my notes, but this is an important term. Every time you integrate, you got to have plus c, because it is not conclusive, or not conclusive. It is not unambiguous. So because there are infinitely many answers to your question, and look at it. Why it is also noticeably a problem, because if I plug in n over the n equals 0 into the last equation, then it will give me a power of 1, which means that a constant term in that sigma, in that summation, the very first constant term is missing, and that term is missing. But why is it missing really? So it is certainly possible to have a function the derivative of which is equal to this function, to f. Okay, so then that's what plus c is. It means that the very first 0th term of our power series is arbitrary. That's what we're saying here. And that is the whole theorem. Okay. Let me make that point again more grammatically to make sure that's what changes about the power series is this. When differentiate, you start with the n equal 1, and here you have to, you're in fact the opposite. You have to insert an extra term. Hopefully, fortunately, it is arbitrary. So as far as differential equations, example I picked that's certainly very simple, and so that algebra would work out as simple as possible. So the idea is to have a model which is a familiar model, but we pretend that it is not. So the rate of change of a certain quantity is equal to the quantity, or is proportional to. So that indicates population growth or anything similar to that, depending on the circumstances. I pick a simpler one, and that is when it is indeed equal to. So I'm talking about a function represented, so it's y equal f of x, and if I translate this into a sentence, I have f prime of x is equal to f of x. Okay, so once again, we pretend that we don't know what the answer is, and we just go on and solve it. once again, not relying, we're trying to have a method here rather than relying on prior knowledge, prior memory of what the answer should be. We will try to pretend that we don't know, and we see if there's a method here possibly that will solve our problem, and that method is power series. So we already know what to do. We just start with function is unknown. So that's what makes a differential equation. It is an equation that connects a function with its derivative in some way, including the simplest way, and you need to find f. Find f, and how do we find it? It's like just always with equations. It is sometimes there is no formula to worry about because, well, if it is a quadratic formula. Oopsie. Okay, that's the end of the projector on the last day. That's nice. Okay, so, well, I will not be deterred. As much as I don't like chalk, I'll have to now finish this example. Okay, so f prime is equal to f of x, and so how do we solve it? We represent our function by power series, and we have, at its simplest is, say, Cn x n. It smells too. Okay. Okay, so I just continue on with the example. I go straight from my differential equation. I need to find f. So fortunately, it turns out that this complexity of functions can be reduced to a power series, which means that all we need is a sequence of coefficients. If we can find a sequence of coefficients, we have the whole function ready. Okay. So how do we do it? We plug in. So I have my left-hand side, right-hand side is this, same thing. And what do I do on the left? On the left, I differentiate it term by term. Okay, so derivative right here. So I will have this summation differentiated. So this is directly the same thing, right? And now I'm applying this theorem. Okay, so I differentiate it term by term, and okay, so I have term by term. We have the formula, so I cannot show it to you, but well, let me do it anyway. Cn xn prime, right, like this, term by term, and we keep going. So we'll have summation n from 0 to infinity. Well, remember it is from 1 to infinity. Differentiating, I have Cn n x n minus 1. Okay, so any questions about this differentiation? So I choose to assume that my function will be differentiable, and it is represented by power series. Okay, so on some interval, on some, say, minus r, on some open interval, negative r prime. Okay, so I plugged in this representation into the formula, so I have derivative on the left, function on the right. I differentiate term by term according to our last theorem. Okay, and I have now what the key is to compare these. It is supposed to be the same thing. And here we are invoking another theorem from yesterday, and that is the uniqueness theorem, which says that if two series are equal, then their coefficients are equal. Okay, so then by uniqueness theorem, the coefficients are equal. So, but it is not so obvious because we have to match them up. We have to match them up because the powers don't match. These two are not matched because the power of this is aligned with x to f power, but this one aligned with n minus first power. Okay, so if we just write them out in the string, we'll see the difference. So let me take these, like here, and I will write them in one string. So it will be C naught plus C1x plus C2x squared plus C3x cubed and on. Okay, that's my function, still my function. And now I take this one, the derivative, the same thing differentiated term by term. So I have like this. It will start with, remember, it starts with 1, which is, so it will be C1. C naught is gone. So I have C1, right? When I plug in n equal 1, I have C1, 1, 0th power. I have C1. Okay, the next one is C2. What is the, I have 2. And I have the power goes up by 1, it will be x. Okay? Now I move on to n equal 2, and I have C3. I'm sorry, moving, I'm going to the next n. So I start 1 to n equal to 1, 2, 3. C3, 3x squared. Okay, and you see the pattern, C4, 4x, 4, and on and on. Okay, so once again, now they are aligned now. The terms are aligned now, and then these are equal. Let me be careful here, like this. Okay, these terms are equal. And, okay, so they are equal, literally. And so, and we have what we end up with, a bunch of equations. How many equations? Infinitely many equations. We have infinitely many unknowns, so that's the challenge, I suppose. Infinitely many unknowns and infinitely many equations. So, but fortunately, it's not too complicated if you just go one by one. Okay, so I start from the first. C naught is equal to C1. Okay, so far so good. These two are equal to each other, but then the second equation is that C1 is equal to twice C2 over C2 is equal to 1/2 C1, which is 1/2 C0. Because they are linked up in this way, I will express every single term, C1, C2, C3, in terms of the only one element, the very first one, C0. So I already did. C1 is equal to C0. Okay, so that's 1. And now I have one more. C2 is 1/2 of C0. Okay, and then I go on, and I look at the third one. I have C2 is equal to 3C3. Okay. So C3 is equal to 1/3 C2, and I substitute this, and I end up with C3 equal to 1/2 times 3 C0. Okay, so as you can see, I'm getting these elements one by one. Okay, so let's do one more. The pattern will become clear. So I'm now using the fourth equation over here, and I have C3 is equal to 4C4, which means that C4 is equal to 1/4 C3. I substitute this, and what do I have? I have 1/2 times 3 times 4 C0. Okay, so you see the pattern. C0. Let me flip this one. C0 appears every time, right, in all of these formulas. The fractions start to grow, so this is 1, and then 1/2, 1/2 times 3, and then 1/2 times 3 times 4. So what are these numbers? It is a 4, so you can tell me what Cn is then. What does this pattern tell us about Cn? C0, right? C0 repeats every time, and what's here? Factorial, right? This is 4 factorial. This 4 factorial, that's going to be n factorial. So 1 1 factorial. Okay, so well, that solves the problem altogether, because now we have every single element is known. Every single element in our sequence is known. So the series is known now, right? We know every entry in this sequence. So I can actually write my f of x as a series, and I can find, as I suggested, I can find every value for every x imaginable. I can find the value of this function. I plug in x into this formula. I look at the series, and I find the value. Okay, so if I cannot compute the whole thing, which is possible, then at least I'm gonna approximate it with any accuracy I want, because we have infinitely many terms. If I get more and more terms, I get more and more accuracy. The only thing that's missing here to assure that this works out is we need to show that this is the series is convergent. So the last step is show this is convergent. And not only that, you need to show that you need to find the radius of convergence. So use the root ratio, say test. We already did. We're pretending that we don't know what the answer is. So we use the ratio test to prove that r is equal to infinity, as a matter of fact. So the domain of this function that we found is in fact the whole real line. Okay, so so that would end the story. So like an example that comes from some vague description of a model that we want to use. We come up with a differential equation over here. We use the idea of power series. We found the power series explicitly, every single term of the power series. Then we show that in fact that it's not only just any power series, it is a convergent power series with infinite radius. So domain is negative infinity infinity. Okay, and then you can stop here, because if you abide this idea that functions or power series are as good as functions, then you're done. If not, then you are lucky, because this is a very simple differential equation, and that's why the answer is simple. And the answer is what we simply take a hard look at our series and we recognize what this is. Like this. I forgot about C naught. So, what is this? How about if I factor C naught out, that helps us to understand that this is a familiar function, the series that we have seen many times. It is the exponential function, so C naught e to the x. Okay, so that's the answer is then f of x is equal to C naught e to the x. The meaning of C naught is the initial value of f. It is that's the ambiguity part, because there is no description in the description, our description of that quantity changing with time. There was no specifically indicated what was the initial value of that quantity. So we solved the problem bigger for every possible initial situation. C naught, right, is C naught is f of 0. Okay, so if you have the initial value, then you plug it in, and you have automatically you receive the you can compute the whole thing. So in general, it's not as easy, because the algebra might be more complicated, but not this part. This part is still easy. It's differentiation is easy, integration is easy. You do end up with a system of equations, infinite system of equations with infinitely many unknowns. So that's a challenge. But if you have a more powerful enough computer, you can solve the problem that has become algebraic entirely. We took calculus and converted it through this into a problem of linear algebra, solving systems of linear equations. That is very big computers that do it very easily, and they are built pretty much to do that. And then you can solve your problem then with any accuracy that you want. Okay, so that's roughly what how this works out. But more examples you certainly need. For more examples, you need to look. You go to take a differential equations course, and it usually comes right after calculus 3. Even though you could probably, if you understand series, for example, then sometimes calculus 2 is enough if you don't go to multidimensional stuff. Okay, so so any questions? Anything else you want to bring up for the final? Okay, then we'll just adjourn, and I'll meet you on Thursday. In between, you either I have a test final on Monday, so that's one way to